When mathematicians and computers need to process thousands of numbers simultaneously, they don't read them one by one. They organize them into structured grids. Take a look at this data table of student test scores. By stripping away the text labels and enclosing the remaining numbers in large brackets, we convert a real-world dataset into a pure mathematical object called a matrix. A matrix is simply a highly efficient container for data. Removing the distracting context allows us to focus entirely on the mathematical relationships between the numbers. To work with these grids, we need a strict standard to describe their exact size. We call this the order of a matrix, and it is always measured by counting the rows followed by the columns. A common hurdle for beginners is mixing up which direction is which. Just remember that rows run horizontally, left to right, exactly like rowing a boat across a lake. Columns run vertically, like the structural columns holding up a building. Look closely at this specific matrix. We count 1, 2 rows across and 1, 2, 3 columns down. That gives this matrix an order of 2 by 3. Correctly identifying the exact order is a mandatory first step. Every matrix calculation you will learn relies on these dimensions lining up perfectly. Matrices come in specific shapes, and recognizing those shapes is how we classify them. The simplest forms are a row matrix, which has exactly one row, and a column matrix, which has exactly one column. Look at these two examples under rectangular matrix. The row and column matrices fit perfectly because their rows don't equal their columns. Contrast that with this 2 by 2 grid. When row and column counts match perfectly, you have a square matrix. You might wonder what happens if a dataset is entirely empty. We represent that with a zero matrix, a grid completely filled with zeros, which can take the geometric shape of either a rectangle or a square. Identifying whether your matrix's geometric base is rectangular or square dictates exactly which algebraic rules you can apply to it in the next phase of your calculations. Within square matrices, there is a specific pathway called the main diagonal. It only exists in perfectly square grids, starting at the top left corner and running directly to the bottom right. In this diagram, only the main diagonal contains non-zero numbers. This pattern is a diagonal matrix. If every number on the diagonal shares the exact same value, it becomes a scalar matrix. When that diagonal is composed entirely of ones, it's the identity matrix. By looking at the rules we just applied, you can observe an overlap. An identity matrix is technically also a scalar matrix and a diagonal matrix, all at the same time. Pause for a moment and picture a 3 by 3 square containing only 5s on its main diagonal. Try to apply those nested definitions to see exactly how many categories it fits into. Understanding these subsets is vital. In advanced linear algebra, the identity matrix performs the exact same mathematical function as the number 1 does in basic arithmetic. Instead of memorizing 8 isolated definitions, we can consolidate these terms into a single logical hierarchy. This flowchart maps our rules. All matrices splits down 2 paths based on shape, rectangular and square. Tracing the square branch reveals nested conditions. It narrows into a diagonal matrix, tightens into a scalar matrix, before reaching the strictness of the identity matrix. Mapping these relationships as a visual tree eliminates rote memorization, helping you build true structural comprehension. Let's test your grasp of this classification tree with a final practice challenge. Here is a notebook showing 2 specific edge case problems. Your task is to determine the exact order and list every applicable matrix type for the 1 by 1 matrix on the left and the asymmetrical 0 matrix on the right. Take your time with these edge cases. Categorizing these structures at a glance is the prerequisite for the operations and equations we'll tackle in the next lesson.